Sorry. We started the recording, sorry about that.
Oh, sorry, you started late. Okay, sorry. So, and then we're gonna finish with a summary and conclusions. So, soil structure interaction. What is soil structure interaction? It is a process in which the deformations of the structure will affect the response of the soil. And in turn, the response of the soil will affect the deformation of the structure. So it is important. Let's see what we have. First, some structural engineers, okay, may consider, let's say, analyzing their structure, assuming that we have supports here. So basically, they're going to close everything, assume, let's say, that this building is built on rock. No deformation, no soil structural interaction. So definitely, this will going to entail no interaction. If we have seismicity here, earthquake or whatever, we're going to have a big problem. The performance will be so different, okay? Then, one step ahead, one step further will be to represent the soil using springs. So to represent the stiffness of the soil and its effect using springs. So again here, we didn't simulate the real soil structure interaction, we just took part of it. So this we can say it's halfway, not halfway, let's say 10% or 20% along the thing. Then if we consider the entire thing, the full soil structure interaction, this is the right thing to do. And actually this we're going to give you the real performance or the real prediction of the performance of your structure. Okay, so here you're going to consider the full interaction. So this is our journey through the soil structure interaction. Okay, so we can totally ignore it, wrong results, bad prediction, not good, or we can consider it partially, but again, partially means some part of it. So it's not good, but let's say 10, 15, 20% along the way. And of course, if we want to consider everything, we need to consider the full soil structure interaction. Okay, however, every one of this, we're going to come with its cost. So the numerical cost and the numerical effort and the expertise of the numerical modeler is very important here when we consider the full soil structure interaction. So let's continue. So in this lecture today, we will gonna explore the effect of the soil structure interaction and the predicted performance of two special geotechnical problems. So I just chose for this lecture two different problems to show you the power of the soil structure interaction. So the first problem here, we're gonna involve investigating the effect of the soil structure interaction and the employed conservative material model on prediction of the behavior of earth pressure balance field driven tunnels, utilizing a case study, real study of Metro Line 2 in Shanghai, China. In the second problem, we're going to do basically the same thing. We're going to investigate the performance of integral abutment bridges. However, we're going to use a case study from New Brunswick, Canada here. So let's start with the tunneling problem first. So this is here the map of Shanghai here. So this is line 1, and the green one here is line 2, which we considered in our analysis. So after they excavated or driven their line 1, they went into line 2. So if we explode this area in here to just magnify it, we're going to see that this is your line 2 here. Okay, so and these are the boreholes available along the. Okay, so as we see, we have so many soil layers in here. Okay, mostly soft clays, soft soils, silty clays. So in general, soft soils. And the tunnel itself, it was composed of 2 tunnels. Okay, so we have tunnel 1 and tunnel 2. Okay, and what we have in hand is the settlement readings or monitoring program, results for settlement, pore water pressures, lateral movement, and earth pressures. That's what we have, as we're going to see later on. So let's refresh our minds. What tunneling involved, or this earth pressure tunneling involved. So if we look into here, this is the tunneling machine. It is kind of conical shape a little bit. And we have here the face pressure. And as it excavates here, the residual or the products of the excavation will be just conveyed in the conveyor here, outside, in here. And as it excavates, create area and moves in, we're gonna create a void space to install the new segmental lining. And then after we put the segment, each segment, okay, along the ring, we're gonna start injecting grout, okay? So if we look into this, from this side in here, we have face pressure, okay? And then we have our lining, and we have grout in the tail here, okay? This grout is not hardened immediately. So we have fresh grout, and this fresh grout will harden by time, okay, as we proceed. Okay, so this is general the thing. So in order to start the model, we use the concrete model available in Plexus. This concrete model was just new. This work here that I'm presenting, we did it, I think, 3 years ago. So the concrete model was just new. So we have first to validate the model, make sure that the model works fine. So we validated the results through tests done by V et al. For plain concrete in 1996, and another test by Mansour et al. In 1999. Okay, so here we have the strain versus strain, and we have those kind of gold dots represent the test results, whereas the continuous green line represents the predictions of the Plexus 3D. So it is beautiful. We can say that it's match beautiful. We were able to capture the performance of the concrete, even post-cracking, which is very important in here, in this region here. So it is amazing. Actually, I had to double check it a couple of times to make sure that everything is fine. As my student right now, she's Dr. Anna Maria Zaki. And this paper is published in the Transportation Geotechnique. I can give you the link at the end for the paper to enjoy reading it. So, also, this is what we are showing here is the 3D mesh of the problem. We have several different layers, as we said before, and we modeled 42 meters of this tunnel in the third direction. Okay, so we use the hardening soil model. So we were going to see which soil model will going to give us the best prediction. So we considered the hardening soil model. The hardening soil model with small strain stiffness, okay? The modified camp clay model and the soft soil model, all in Plexus. The soil parameters utilized for the 4 conservative models in short and long-term conditions were obtained from the conducted laboratory experimental results. So we have this results, and accordingly we obtained all of the required parameters for each of the models. So here I'm just summarizing what this entails in 3D. So as we said, we have face pressure here that will be applied, okay? And we have the weight of the conical shape earth pressure machine, okay? This is a shield of the machine. And as it progresses, as the machine progresses stepwise, okay, as it installs the new liner ring, the new ring, the grouting will gonna continue, we're gonna start, sorry, with fresh grout, and then as it proceeds, this grout will be hardened, so it will be assigned the hardened ground properties, okay? And then the process will gonna just repeat till we finish it. Just for your information, each run took from us on a very powerful server that we have in our group, it took us 7 days continuous. Why? Because we are modeling everything. We are modeling the true construction procedure. We modeled as well the connection with the, so we modeled the segments, the tunnel segments, and the connections with the ports. So everything is being modeled in here in details. Okay, so let's see what are the monitoring results and their comparison to the predictions of our model. So we have the results of the surface trough after 1 month and after 3 months from the general height time. Okay, so the experimental results are shown here and this orange squares, okay, in here. This is after 1 month and this is after 3 months, okay. The black continuous line represent the hardening soil model with small strain. The brown one represent the predictions of the hardening soil model, whereas the blue one represent the modified can clay, and the green represent the soft soil model. As we can see here, the best one of them that mimicked the performance of the settlement trough is the hardening strain model. Okay, so after 1 month, the predictions were within less than 0.5%. Okay, 3 months, same. Okay, however, here for the 1 month, the hardening soil model was 4%, the maximum. Okay, for the soft soil, it was 27%, and for the modified can clay, it was way, it was 32%. Actually, in the 3 months, things get much worse for the other ones. So from here, we can say that the hardening soil model with small strain outperformed the rest, was the best. Let's move to the Plateau Crusher. So this tunnel here was fitted with different piezometers at different depths to monitor the progress of the Plateau Crusher with time. And here we have the results of 200 days or 180 days of monitoring. So basically 6 months of monitoring from construction to the end. So here we have the predictions of piezometer 1, 2, 3, 4, and 5. So in a different location over the tunnel here. So again, we can see that the performance of especially near the tunnel here, the performance of the hardening strain model with small strain is the best, as we see. Okay, same thing here for the lateral movement of the tunnel and the transfer direction. Okay, so as we see again here, this orange squares represent the field case study, whereas our black here represent the hardening soil model with small strain, and we see that it was the only one that was able to mimic the lateral movement. By the way, here we are talking about 2 or 3 millimeters, so it's very, 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 very precise. So when we have this difference here is less than let's say less than 1 millimeter or so. Okay, so the prediction is great. Also, this liner was instrumented with different pressure gauges, pressure cells, okay, over the tunnel, and here are the predictions again during construction of the different cells. And we can see a perfect match, excellent match of the pressure that was obtained by the hardening soil model with small strain. Okay, so here this showed us the importance of the soil structure interaction. We were able to mimic the behavior exactly for this very complicated tunneling problem. This is tunneling in very soft soil, so everybody who works in tunnels knows that this is a very challenging problem. Okay, however, the powerful of soil structure interaction, the power of soil structure interaction, and the use of appropriate soil model was able to help us to predict the results very, very nicely. Okay, so let's move to the second part of this lecture, which is considering the Industrial Park Route 7 Underpass Integral Abutment Bridge case study here in New Brunswick. So let's introduce what is integral abutment bridge, because maybe some engineers listening to us right now don't know exactly what is the behavior of it. So they are Bernoulli structure in which portions of the superstructure and the substructure moves together into and away from the backfill to accommodate translation and rotations with no expansion joint and bearings. Everybody works in the bridge industry knows that bridge bearings are, and the connections here are the worst. So they need lots of maintenance. It's very costly, okay? Especially in countries in the north here, like United States, like Canada, like Northern Europe, whatever. We have huge fluctuation in the temperature, and accordingly, we are going to have use de-icing salts and stuff like this. So accordingly, we need frequent maintenance, and this is huge cost. Accordingly, they moved to more or less to the integral abutment bridges, where the structure and the abutment of the bridge are being poured together, are working as one structure. So eliminating the need for any joints or bearings or for whatever. Okay, so also, the simple geometry of the abutment with single row of pile, which will be very typical, and it results in a very fast construction as well. Because basically, as we're going to see in the next slide, we're going to just use one row of H piles, and that's it, and we support our abutment on this. So again, it's very, very, very useful to eliminate the expansion joints and the bearing, which we're going to significantly reduce the construction and maintenance costs. So, in general here, integral abutment bridges are characterized by their complex soil structure interaction of the abutment wall and the foundation, as they are subjected to cyclic loading. So, let's say in the winter, the concrete will shrink, right? So, the structure will gonna move away from the soil, and this will gonna constitute more or less an active earth pressure. However, during the summertime, the concrete will get expand, and accordingly, you're going to push on the backfill soil and will be in its passive mood. Okay? So, the objective of this part of the lecture here will be to understand the effect of the soil movement of the bridge on the soil structure interaction. We're going to utilize a two-dimensional finite element analysis. Okay? We will also explore the effect of the employed soil model again to see its effect on the prediction of the earth pressure within the soil mass, as well as the earth pressure acting against the abutment, which undergoes cyclic loading. Okay? And also in this section here, we're gonna show and we're gonna demonstrate that the simple Moore column or the elastically perfectly plastic soil model that's being used frequently by several engineers to model such problem is not good, and it will not gonna accurately describe the behavior. It will not be able to do this. And we need more advanced soil models like the hardening soil model and whatever to be used. So let's talk about the case study that we have in hand here. So this is our apartment here, okay? So on this apartment here, rests a girder, which is 1,800 millimeter deep girder. So it's a large girder here that supports the bridge deck here, which consists of 225 millimeter of deck slab overtopped by asphalt. And then at the back here, we have the approach slab, and we have draining material in here. And then we have a backfill, just a polo backfill to backfill behind the drain material. And below is supported on H piles, okay, suited in their weak axis. So we give a flexibility of movement, seasonal movement of the abutment. So this abutment here was heavily instrumented with strain gauges, with thermocouples, with contact pressure cells, tilt meters, deformation meters, and you name it, was heavily instrumented. So we have, so this will help us to develop a comprehensive model that we can validate it using several things, not only one. So basically here, this is the wall, the retaining wall. So we have the earth pressure at 3 levels, and we have the tilt meters here at 2 points here, okay? This is the monitoring results that we have. So here, this is the change in the translation and the movement of the abutment versus the time. Okay, so this direction here below means that the abutment moved toward the backfill. So toward the backfill, this means that we are in the summertime. Okay, up here, this means that the movement was away from the backfill, or it's in active mood, means that we are in the winter time. And here, this is the variation of the temperature. As we see, the temperature varies in the summertime of near 30 degrees or maybe 31 degrees or so to a typical Canadian weather of huge -0. Okay? So the changes and the pressures as well, we have it here for the different sensors. Okay? So we have two models here, soil models that we used. The first one, which is the elastic perfectly plastic soil model. We all know this model. You just need your elastic model E, and accordingly, you need your phi and C, and that's it. So it is perfectly plastic after. Okay? The second model, which is the hardening soil model, which is suitable for this kind of loading, especially because it has three different stiffnesses. One stiffness, E50, that represented a triaxial loading stiffness, okay, which we're going to determine the magnitude of both the elastic and the plastic strains. We have E odometer, which is the odometer loading stiffness as well, which we're going to account for the plastic strains due to the primary compression. And finally, we have the E unloading, reloading, which in conjunction with the Poisson's ratio will be able to determine the ground behavior under unloading, reloading conditions. So basically, this soil model is comprehensive in terms of the nature of the loading itself, the soil that will be loaded. So we know that the stiffness of the soil during loading is different than its stiffness during unloading. Constrained stiffness is different than the stiffness interaction. So this soil model here is capable of addressing all of this. So we developed two Plexus models, okay? We apply to those Plexus models here the cyclic thermal displacements, okay? And we monitored the earth pressures, okay? We have one model, okay, that was utilized using the hardening soil model, the one that we believe it will be predict their behavior better. The second model, which used the Moore column, that soil model, or the elastic perfectly plastic soil model, that we want to demonstrate that is not sterile. So these models follow the same geometry layout construction procedure of the full-scale abutment, and the results were compared with the field measured earth pressures. Okay, so stage construction very quick. First, we installed the. Oh, sorry. Just give me that. Still only 2 minutes or 3 minutes. I don't want to overrun, but just circle that. So then we simulated the excavation. Then we placed the pile platform. Then we put our pile in sand. Then we're going to continue with the whole construction sequence. Okay, till we have at the end here our full apartment with the loads coming from the main structure. Again, you can read the paper here. I'm going to send the link for the paper. You can enjoy reading it with my student, Mr. Francois Duguay. Okay. So in this problem here, this is the applied displacement. So it was superimposed displacement that represents the monitoring cyclic displacements. And then we were going to read the pressures, earth pressure in the back of the wall, and compare it to what we have. So in here, we have the results of we are showing the results of the second model, which is the Moore column. Okay, so here we have the predictions of the field. Okay, so in the first year, we have the predictions from 3 years. Okay, in green here, we present the first year. In purple, we present the field results of the second year, and in red represent the field results in the third year, okay? The Plexus result of the respective things are in dotted lines, okay? And this are presented along the height of the abutment. And here we are presenting the seasonal changes of the S pressure. So the difference or the movement of the S pressure. So, and these are the three locations that we measure the pressure at. So as we see, those three are the S pressures in reality. And this was the S pressure that we obtained using the mode column. If we consider the error or the difference in predictions here in the first year, second year, and third year for the 3 points or the 3 locations, we're going to see that we had almost an error, estimated error of about 33 or 34%. Huge, definitely not acceptable. Let's see when we considered a better prediction model. So as we see in here, the predictions of the Plexus and the field results are almost identical. Only difference here is 3-4 kilopascal, which is basically nothing in the difference. The error is less than 10%, okay? And basically, actually, this is at the very lower point. The other points, the error are almost matching. There is almost no error. We're talking about 1%, 2%. So this is perfect prediction. So just to summarize and conclude, okay, so we presented here a detailed finite element analysis using Plexus 3D and 2D to examine the SoilStructure interaction performance of 2 special geotechnical problems, the tunneling problem and the integral abutment bridges. What we can take from here is that for the tunneling problem, we consider 4 different advanced soil conservative models. However, the hardening soil model small strain was superior to the other models under consideration in modeling the soil behavior. This superiority is attributed mainly to the ability of the model to mimic the variation, the stiffness that accompany the changes in the strain level, especially at small strain levels, which is very important in tunneling problems. However, for the integral abutment bridge problem, we showed that the simple elastic, perfectly plastic mode column model that's being used frequently by engineers to design such problems here is not capable of simulating the soil behavior during the cyclic loading and unloading cases, and that the hardening soil model was a better soil model to use. The maximum value of error of the hardening was much lower than the 12%, okay? And whereas the error for the mode column soil model was 34%, 1/3. So definitely it's not. So thank you so much. It was my pleasure today to be among you and to present. Thank you so much.
Thank you very much for this amazing lecture.
3-4 minutes extra. I'm so sorry for that.
No. Any questions? If you have.
Hi, Mahmoud. Yes, I have a question.
Yes, hi, Mohammed. Go ahead.
Hi, Doctor. In the tunneling part, I was wondering, like, in your model, do you consider the lining as a waterproof because you add like the grout between the soil and like the concrete lining, or you allow it as like a kind of a drain because of might be like some permeability or so?
Yes. No, we assume it's impervious, so there is no water.
Okay. Okay. And also, like, Doctor, is there any effect, because like I found that there are 2 tunneling, is there any effect like for one tunnel on the other, or like the distance was like wide enough?
Yeah, exactly. Maybe I must presented this or presented very quickly. So first we mined the first tunnel, was mined in, and then we put the second tunnel. The effect is not that huge because the tunnels were located 18 meters away from each other. So almost that was 3.5 meters away from each other. So the effect was not great. But if you don't tunnel, your prediction will be of less match.
Okay. Thank you, Doctor.
You have to consider that thing. You are very welcome. You know the Muhandisin building that has some problems, maybe last year, whatever, would have been told pretty much with such modeling technique. So if they modeled everything before they tunnel it, in details, like what we did with the Chennai case here, this will have saved the building, which is multi-million building.
Oh. Yeah, this is the one at Zamalek.
Yes, in the Zamalek. Sorry, I said once.
Yeah.
I'm from Alexandria. So
Yeah.
one place, Cairo.
Okay. Thank you very much for this interesting presentation.
You're welcome.
Ahmed, I think you need to ask a question.
Good morning, Dr. Hany. I hope you are doing well during fasting. I have two quick questions.
Please.
The first question is related to the forces applied to the tunneling in the first part of the presentation. I observed that you applied a drilling pressure during tunneling, but I'm wondering if there are different forces were applied to the tunnel.
So the tunnel in the face pressure, you have a face pressure which is linearly increasing with the depth of course, okay, to resist the pressure from the soil. Also, we consider the own weight of the tunneling machine itself, okay? And then you have the jacking forces that being applied. So you have the jacking forces, you have the face pressure, okay? And then also you consider the grouting pressure as well. You consider that grouting pressure. Have I missed any? I think that's it. You can refer to the clear reference of this case study. Actually, it's very nice. Not because it's my work, but really I enjoyed it. It's very nice case study. And it's published in Transportation Geotechnique, I think, in 2019 or 20, I'm not sure. 2019, and Transportation Geotechnique 2019. Anna Maria Zafin and Hany Naggar.
Yeah, because what I witnessed during the presentation that you only mentioned the face pressure, so I was wondering because according to my my work with tunneling that we always apply jack thrust and we apply also the segment which is the lining pressure, and in case if there is like a shield like a steel shield until we apply this pressure also.
Yes, we simulated this. We simulated all of this.
Yeah.
My second because it was just I'm presenting two cases, and the time is only allowed us to only have a minute, so that's why I was a little bit fast. Sorry for that.
Thanks, Doctor. My second question is a general question. It's related to choosing the numerical model or the constitutive model for the analysis. Usually, we have like a lake of parameters that require for the sophisticated model, for the sophisticated models. So I'm just curious, how can we like choose these parameters and how we can control the uncertainties of the finite element, especially with this lake of soil parameters?
Very good question. Very good question. So first, what you need to do, you first need to validate your model first, mechanically. So you need to consider case study that you know the results and the monitoring results that you rely on, and the soil are more or less closer to your soil. Okay? So let's say if you have tunnel mainly and clay, whatever, you're going to go with the London clay cases. You have several of them. Then you're going to, after validating your model, you know that your model mechanically works fine, everything is fine. You're going to start looking into the parameters, soil parameters for each. You are going to try to have, of course, for such projects, you have the luxury of ordering A-class soil testing. So you're going to have lots of tracksuits. You can get this. The contractors cannot say, no, we don't have this. We are talking about billions here, right? So you have a full suite of soil testing that you can apply. When you are in doubt or when you are missing some data, you're gonna go with some correlations for the similar soil. So you need to dig a lot in the literature. So what I'm always saying that if the job is assigned, let's say 100 hours to do the design, okay, you need 30 hours of reading literature, what others did in the same soil, same conditions, what problems they faced, and what's going on. So you need to educate yourself and not only, let's put it this way, refresh your mind for every project. So you need to read and read and read and read and read. So it's very, very important to do this. And this is the only way that we have. Okay?
Okay, thank you very much. I have a related question to this part, which is, if we are performing or conducting like a centrifuge test or a shaking table test, usually when we start to calibrate or validate the numerical model, there will be also uncertainties about the setup of the test and also the measurement, especially if we are working with the soil structure interaction. We will find there is a lot of disturbance, especially after installing the structure. So when I'm like, if there are a lack of measurement, especially after installation, and I am calibrating the numerical model. So my question is, there could be uncertainties from the measuring of the parameters, but what could be other factors that can affect, or I can like accept a threshold for the errors in the numerical model?
Okay. Look, what you cannot forgive is the construction sequence. So you need to know exactly the construction sequence, even if it's wrong, let's say, but you want to validate, right? So your model has to follow the same construction sequence that was done in the centrifuge. The problem with centrifuge, it is so sensitive kind of testing and needs lots of experience. So for example, I had one of my PhD students, Dr. Naim. He did centrifuge in Memorial here, and it took considerable time in order to understand how the system works and how we're going to model everything and what kind of scaling effects would be involved. And there is always a kind of trade-off. So scaling effects, yes, always will be there. But otherwise, we don't have a full scale of the problem to consider. So having the problem in full scale is going to cost billions of dollars. Nobody's going to invest this money in this. So